Hello, welcome to the video on function and relation analysis. This is going to be a lesson on this topic, and let's go and take a look at our objectives here for this lesson. So the first thing we're going to do is we're going to determine the domain and range of a function graphically. Okay. The next thing we're going to do is we're going to find the domain algebraically within the real numbers, the set of real numbers. Next, we're going to determine when a function is increasing, decreasing, or constant. And then lastly, we're going to take a look at explicit and implicit functions. All right, so a lot to cover here, and we have a lot of important things in this lesson. And probably, they're all important, but I would say one of the most important is what we're going to discuss first. And that is, we're going to determine the domain and range of a function graphically. In other words, here I have a picture, or excuse me, a graph of a function. We can think of it as any type of function. Okay, and we know it's a function because it passes the vertical line test. Now, given this particular graph, I'd want to be able to describe the domain and range of a function. Now, we're going to be describing all of our domain and ranges here using interval notation. So just kind of a little heads up, so you make sure you've watched those lessons and you're familiar with that. So before we get into this, I want to give you a chance to write down these kind of definitions here. So I want you to go and pause the video, write this down, then I'll come back to this graph. Okay, so the first thing is, it says the span of the graph with respect to the x-axis is the domain. And then the span of the graph with respect to the y-axis is the range. Okay, so x-axis is going to have to do with the domain, and y-axis is going to have to do with the range. In other words, we're going to be focused on the x-axis when we're trying to figure out the domain graphically, and we're going to be focused on the y-axis when we're trying to figure out the range graphically. All right, so let's go back here and take a look at this. Okay, so I'm going to try to explain this in language that's kind of easy to understand. And trust me, oftentimes students this is a little confusing initially for a lot of students, and then finally like a light bulb will go on and be like, oh, okay, now it's very easy and I get this, okay? So kind of hang in there and I'll do my best to kind of explain this. All right, so here I have this graph, okay, a graph of a function. So let's focus first on the domain, okay? Well, the domain, you can kind of think of it as this. How wide, okay, how wide is this graph with respect to the x-axis? Okay, so let's go ahead and just focus on the x-axis, all right? So think about this. These arrows indicate that this graph is going to continue to go and keep getting wider and wider and wider and wider, okay? So one way to kind of think of this is like, well, is this graph going to span the entire x-axis? Kind of think of it this way, okay? When you're thinking about the x-axis, if I kind of drew a line down from the graph where it touches a vertical line where it touches the x-axis, like where is it spanning, okay? Well, you can see here that this graph, and this graph is eventually going to keep going higher and higher, okay? If you think about it, this sketch, this function, this graph here, is going to span the entire x-axis. Now, you're going to have to get this graph is going to have to go very, very, very high and steep to hit these points, but it's going to hit these points here. In other words, somewhere way up, beyond this, what we can see in this graph, if I go up here, it's going to hit this sketch. Okay, so graphically speaking, the span of this graph is the entire x-axis, okay? In other words, all x's, okay, will be found on this graph, okay? Now, hopefully that makes sense. If that makes sense to you, okay, then I think you're going to be well on your way. So the x-axis, or the x values, recall, are the independent values in a function, okay? It's what we could put in. It's the domain, okay? So being that all the x values on this particular graph, okay, are represented, the domain is all numbers on the x-axis, i.e. all real numbers, okay? So do you recall how to express all real numbers, okay, using interval notation? Just a little pop quiz here. All right, so the way we do this, remember, is we were going to go from negative infinity to positive infinity, both open intervals. So if you don't understand it, you need to go back and review the lesson on interval notation. In other words, this is negative infinity, this is positive infinity. All of these numbers in between negative infinity and positive infinity are represented in the domain. Okay, so if you understand that, then basically we're going to do the same thing. Let me kind of erase this here, but now we're going to focus on the range, okay? And we're going to do the same thing, but instead of focusing on the x-axis, okay, we're going to try to do what? We're going to look at the span of the graph, okay, how wide it is, if you will, with respect to the y-axis. Okay, now this is going to be a little bit different here, okay? So maybe I'll kind of give you a chance to see if you can figure it out on your own. Okay, give me a quick second. You may want to pause the video. What I'm looking for is the span. Okay, basically we're doing the same thing, but instead of using the x-axis, we're using the y-axis. Okay, I'm going to go ahead and see if you can figure this out. Okay, so if you look at the graph, this graph, okay, and it looks like it's some sort of quadratic function, is only spanning the y-axis, the positive y-axis, only this part, okay, going up. All right, it's not in the negative territory. And one way you can think about that is maybe just drawing, instead of vertically, we can just kind of draw horizontally. Okay, we could see that these points here are touching the y-axis in the positive y-axis part of the xy coordinate plane. Okay, so how can we express that using interval notation? In other words, the y-axis, again, or the y variable, is a dependent, okay, variable when we're talking about functions. And remember, the dependent variable is the values represent the range of the function. Okay, so excuse me. So in this particular example, you can see that the graph is spanning along, with respect to the y-axis, only the positive y's, or the positive real numbers, from 0 going all the way up to what? Positive infinity, correct? Okay, so how can I represent that? Well, the range then would be, it is hitting 0, okay, it is at the origin, so I would go ahead and put a bracket 0 comma positive infinity. Okay, then open parentheses. Remember, parentheses are always found on infinities, okay, and negative infinity and positive infinity. All right, so hopefully that makes sense. Another way we could express this, and this is interval notation, is the domain would be all real numbers. Okay, that would be one way of seeing it, or all the set of real numbers, and then the range would be all y's greater than or equal to 0. So if you are able to kind of see it this way, then that's excellent. All you have to do is go ahead and write this in interval notation. Okay, so we're going to be practicing this a lot in example sets. So make sure you go through all those problems. But if you kind of understand the gist of this, then I think you're going to be fine with the example set problems. Okay, let's go down. And now let's talk about finding the domain of a function algebraically within a set of real numbers. Now, this is important that I emphasize real numbers, because there are other numbers in mathematics, namely complex numbers that you're probably already familiar with. So right now we're only talking about real numbers. So what we're kind of, the way to kind of think of this is the domain, remember, is the set of input values, and I'll get to these restrictions here in a second. But basically, the domain is the input values into a function. Like, in other words, what values were allowed to put into a function without the function kind of blowing up. And so I kind of like to use that terminology. We're like, hey, what's going to break this function? Well, when we're talking about real numbers, there's two conditions that can break a function, okay? And these are our restrictions. These are the things that we need to stay away from. So I'm going to give you a second to write these down, then we'll go over this. Okay, so domain restrictions across the real numbers. So the first is any value that we plug into a function that causes the denominator to be 0 will break the function, okay? So it's not allowed. The second thing is any value that causes a negative value inside of a square root or even a root is also not allowed. So these are the two conditions when we're talking about the real numbers that we have to stay away from in terms of our domain of our function. Okay, so knowing that, let's take a look at this problem here. So do we have any square roots? No, so our second condition is not going to be an issue. But is there a value, okay, is there some input value, i.e. a potential element of the domain that could cause the denominator here to be 0? And of course there is. It would be x would be equal to -5. So if I found f of -5, or was attempting to, I would get what? 0. I would get 1 over 0. I would have a 0 in the denominator. So that would break the function. So -5 cannot be in the domain. Okay, cannot be in the domain. So how can I write that? Well, I'm going to go and give you two ways. We're going to, like I said, I want you to get really good with the interval notation. So you can say there's two ways you can do it. You could say the domain could be all real numbers with the exception of x cannot be -5. So that's kind of like one type of notation you can do. But the second notation, the interval notation I want you to get used to, would look like this. It would be all numbers except for -5. So we would start from -infinity, we would go to 5, not including 5, and then we need 5, but not including 5, to positive infinity. So these are all the numbers, but this is what we call a union when we're talking about set theory, okay? So I need to put a little u here. It's basically union together, or kind of welding together. I'm talking about all these, this set of numbers, and then this interval, these sets of numbers together. And this is kind of a long way of saying all numbers but -5. Okay, so you need to be familiar with this notation, this union. And as you get into more advanced mathematics, we'll get into union and intersection and subsets, etc. But the union is going to become very handy when we're talking about expressing intervals and ranges, etc. All right, so let's go down and take a look at another couple examples. So this first one we did, okay, pretty much this shows the condition of having 0 in the denominator. Now let's take a look at a function that has a square root. So what we're going to say here is that, well, listen, I can plug in anything into this function except for values that's going to cause this value underneath the square root to be negative. Okay, so how do we figure this out? Well, this is pretty straightforward. What we can do is just use inequalities. So we can just say, okay, 2x minus 8, you cannot be negative, so you have to be 0 or positive. So we can just use an inequality here to kind of help us out. So 2x minus 8, you have to be greater than or equal to 0. Now we just solve that inequality. So that's going to be 2x is greater than or equal to 8, or x has got to be greater than or equal to 4. Okay, so this is the condition or the restrictions that we have to describe in terms of our domain. Now let's go ahead and write that in interval notation. So I could be 4, in other words, it could be 4, so I can use a bracket, and it's got to be all numbers greater than 4, so that's going to be going towards positive infinity, and that'll be the open parenthesis there. Okay, all right, once again, you can always watch this again, take time, think about it, and then clearly in example sets, we're going to do a lot of practice problems, and you'll get this. Oftentimes with this particular topic, function and range analysis, students, this is kind of their first maybe exposure to these concepts, so it's kind of a lot coming at you, or students in at least in my experience. It's new, but you will get it, and you need to get it because this is really important stuff. Okay, really important stuff. All right, now let's take a look at how to determine when a function is increasing, decreasing, or constant. This is actually pretty easy. I'm going to go ahead and give you a chance to write this down. It looks probably more intimidating than this actually is. So let me just go ahead and give you a chance to write this down, then we'll talk about it. Okay, so a function is increasing on an interval when you have x sub 1 is less than x sub 2, or within the interval, and f of x sub 1 is less than f of x sub 2. Okay, I'm not going to read the rest of this here, but this is how you would say that. X sub 1 is one particular x value, x sub 2 is another particular x value, and f of x sub 1 is when we take that x sub 1 value and plug it into a function, and then f of x sub 2 is when we take that x sub 2 value, plug it into the function, etc. Okay, so I'm not going to read all of this, but let's talk about what this means. Okay, the best way I can describe this and make this really easy is, I'm going to just use a different color, is think of slope of a line. If you remember back when we were talking about graphing lines, linear equations, a line that went this way had a positive slope. Okay, you could think of functions that are increasing or going up from left to right as I'm looking at it as being increasing. It's the same thing. Okay, so this is a positive slope. This would also be an increase. This function is increasing in this direction. All right, so let me go ahead and just erase this. Okay, so if you remember that, then you're going to be fine with this because it's the same kind of concept. But I do want to speak of the technical definitions here, so we'll get into that in a second. Likewise, if I have a function that's going in this direction, it has a negative slope, this would be decreasing. Okay, so this is going to be a decreasing function. And then lastly, if I have a straight line, this would have a zero slope. This would be the same as a constant. Okay, so let's kind of write this down. So this is a function that is constant. This is a function, if it's kind of going in this direction, falling from left to right. If you kind of think of it as if it had a negative slope, is decreasing, and then functions are kind of going this direction, which would have a positive slope, are increasing. Okay, now why are we talking about increasing, decreasing, and constant functions? Well, all of this is really going to start coming into a lot of importance when we eventually start talking about calculus. And in calculus, one of the main things we do is we try to determine the slope of a function at a particular point. Okay, so if you recall, we're talking about slopes. A function or a graph is going to either be increasing, decreasing, or constant. It can't be anything else. So knowing, not having the graph, we can use these algebraic definitions to kind of figure out, hey, where are the intervals where a function is increasing or has a positive slope, decreasing or has a negative slope, or constant, which is basically horizontal or flat. So these kind of go hand in hand, and this is all kind of getting you kind of ready for the study of calculus. Okay, so that's why we're kind of doing this. All right, so let's go down, and if you have this written down, let's go ahead and actually take a look at this, how these definitions play out. Okay, so here I have kind of a branch of a function. It could be any function, but I just want to show you how, if you look here from the previous graph, it's kind of going in this direction. So that would kind of have like a positive slope. So positive slope, the graph would be increasing. So it's kind of increasing. It's rising from left to right, if you will. Can you kind of think of it that way? Now, by the definition, you can see here, x sub 1, okay, this is less than x sub 2. All right, now, so x sub 1 is less than x sub 2. Let's just give these some values here. Let's say this is 2, and let's say this is 4. Okay, now when I plug 2 into my function, this is the x value. When I plug it in, I'm going to get the y value here. Okay, so you can see that when I plug in x sub 1, that y value is going to be less than when I plug in x sub 2. All right, so when you have that scenario, let's go back up to the definition. When x sub 1 is less than x sub 2, and you plug them into the functions, and you get f of x sub 1 turns out to be less than f of x sub 2. Okay, algebraically speaking, if we just didn't have that graph, on that particular interval, this would be increasing. All right, so you can kind of see it in this particular manner. Of course, we'll see this and the example sets to follow. But if you kind of understand that, then you'll, basically it's the same thing here with the rest of these definitions for decreasing a constant. So again, we have x sub 1 is less than x sub 2, but this time it's different. When we plug in x sub 1 into the function, it turns out to be greater than x sub 2. Okay, when we plug that into the function, this is actually less than f of x sub 1. All right, but graphically speaking, just look here, right? This appears to have a negative slope, so it would be decreasing. So it's important that you do understand the algebraic definitions, but if you're not sure, just look at the graph and say, oh, okay, this is falling from left to right. It has a negative slope, so it's decreasing on this particular interval, but you need to back that up with the algebraic definitions here. So just follow them strictly, and when you plug these values into your function, you'll be able to kind of determine that. And we'll, of course, do the example set practice problems later. All right, the constant scenario, very easy. When you have a graph that's basically flat, horizontal, it's constant. So it's not increasing or decreasing. And that definition is pretty straightforward. So if you have x sub 1 and x sub 2, let's go back to the definition here. You can have, there's no condition where x sub 1 has to be less than x sub 2, or as long as you have two separate and unique values along the x-axis and within that interval. So x sub 1, if you plug that into your function, you get this value, and then we have a different x sub value in that interval, and we get the exact same y value, then you have a constant scenario. Again, you can kind of think of this as a line that has a zero slope. In other words, it's flat. Okay, so we would describe this as a function that is constant. Okay, so again, why are we doing this? This is all built up into your study of calculus. All right, believe me when I tell you, all of this stuff to function and domain analysis in terms of seeing, determining the domain or range of a function using interval notation. You'll see this again for sure. Okay, especially if you're going to be taking calculus. All right, so let's go ahead and talk about the last thing here. This is not too complex. But again, we're going to be talking about a topic that we're going to see in calculus. But let me go and actually talk about it. So we want to go ahead and define and explore explicit and implicit functions. So this is pretty straightforward. Basically, an explicit function is a function that is given in terms of the dependent variable, i.e. y equals, or f of x is equal to, and then all your stuff's over here. It's basically what you're already used to when you see a function. We just never really called it anything else. We just said that this is a function, but functions can be written in two forms. They can either be written explicitly or they can be written implicitly. So let's talk about an implicit function. And again, this is in your study of mathematics, you really haven't seen functions written in this manner too much. But an implicit function is a function in which the dependent variable, which again is x, okay, or excuse me, y, has not been given explicitly. In other words, this is the dependent variable. Y is dependent on what the value of x is. All right. So basically, if you see a function where you can replace the f of x with y and it's y equals, that's an explicit. If you see it written in any other way, you can kind of think of it as an implicit function. Let's take a look at two examples, right? So here I have y equals x squared plus 1. So this would be a quadratic equation. But if I write it this way, f of x, remember y is the same thing as f of x, I can write it like so. Okay, so if I see this function, this means this, so y, the dependent variable, is given explicitly. In other words, I have y equals, so this is an explicit function. It's really as straightforward as that. Now, here I have a relation or a function that is not written where I have y equals. Okay, so this would be an example of an implicit function or relation, because oftentimes when things are written implicitly, you may not be able to write them as a strict function. Okay, so remember, all functions we're studying the broader topic of relations. Some relations are functions, but you can use this terminology in terms of both functions and relations. Hopefully that kind of made sense to you. But basically here you don't see y equals, okay, alone. We have x squared plus y squared equals 1. So this would be an example of an excuse me, of an implicit function or an implicit relation. Now we can try to convert this or rewrite this in terms of an explicit form. So the way we would do that, we would solve for y. So I can go y squared equals negative x squared plus 1. I'm just going to move that x squared over, and then I would take the square root of both sides. So I would end up with y equals plus or minus the square root of negative x squared plus 1. Now looking at that as a function, I have f of x is equal to plus or minus the square root of negative x squared plus 1. So when I ask you to be able to write a function either in its implicit or explicit form, you're going to be going from something like this into something like this. Okay. Now I want to go ahead and just tell you very briefly why this really is important. Again, you won't see this fully play out until you take calculus, but in calculus we do something called finding the derivative of a function. And oftentimes when a function is in explicit form, it's more difficult to find this derivative, and so we end up having problems oftentimes. It's better for us to write, in many scenarios, to write the function in its implicit form, and then we have other tools where we can find the derivative of these functions much easier. And just so you know, the derivative of a function in calculus is basically an equation for the slope of that function. It's an equation of the slope anywhere along that function's graph. I'm kind of getting way ahead of what we're talking about here, but I want to kind of link together the concept of slope, increasing functions, decreasing functions, constant functions, implicit, explicit functions, etc., and while we're studying it. Again, it's all to kind of get you really ready for study of calculus. Okay, so again, it's important that you study do the practice problems, but let's go ahead and review what we learned in the lesson. So in general, finding the domain and range of a function or relation graphically is preferable to using algebra. When you have the graph and you know how to kind of like define those spans, it's really good. That's why graphs are really important to have and make our life so much easier. So if you have the graph, you can define a domain and range pretty much easier than you can just using algebra. Okay. Functions have restrictions on their domain within the set of real numbers. Remember, when we're talking about the set of real numbers, there's two conditions. One, we can never have 0 in the denominator, and the next is we can never have a negative underneath a square root or an even root. Okay, so we have to stay away from those two restrictions. The next is intervals on a function will either be increasing, decreasing, or constant. Again, think of the slope. So increasing is like having a positive slope, decreasing is like having a negative slope, and constant is like having a slope of 0. And lastly, functions are usually expressed as explicit functions, in other words, y equals. However, implicit functions are easier to work with in more advanced math like calculus. And I really hope that if you're studying this level of math, that you do take calculus. Calculus is such a cool subject. I mean, it solves just like real world problems that are really, it really does, I think, for a lot of students come to this kind of apex, this peak of point of like, oh, this is why I've been studying math for all these years, so I can solve problems like how calculus solves, because calculus really takes a look at real life kind of more complicated problems. It's such a great math. I really do encourage you to continue to study. And if you do get to calculus, obviously you're going to need to know the things that we've discussed in the lesson. All right, so I can't stress to you enough to be doing the example set problems. So keep working hard, and we'll see you soon.